it gets a little hard to come up with slides for statistics, if that makes sense. So it's, you can put all the words and stuff, but mostly it's just working through and figuring out the formulas. So good morning, Christy. Did everybody have a nice weekend? Last week was kind of weird. We had Wednesday off because it was Julio Cesar Chavez, and then we had Friday off. I think technically because it's Good Friday. I don't know if they say that or not. I think they always just say it's kind of a holiday that they give people. So last week was a little funny, but hopefully you guys had a good break. So you can see here I put up the t-tests, okay? I just want to look at the syllabus real quick. Sometimes it's good to check in on the syllabus, right, and see where we are. We are already in week 11, if you can imagine that. All right, and yeah, we're in t-tests. Here it's saying that this week we would start 2 samples. We're really starting a single sample, which would be here in chapter 9. So this one, the 2 sample design might get pushed down here. I'm not real sure. So we'll see. No stress though. Okay, we still have another week before our next exam. So we're doing good. For anybody, probably nobody here attending class today, but anybody who hasn't submitted the Z-score homework, of course, I'm still accepting that. Turn it in and I'll get those grades in. I will post a homework for kind of just testing our knowledge about some of these things, the t-test and the various definitions and the t-table, kind of all of the stuff that we've learned this far, okay? So let's see. So like I said, this set of slides that I put up here covers the t distribution, and just to go back over what we talked about last week just a little bit, so we can remember and reorient ourselves about what it is that we're doing. The t distribution is used when we do not know like the population standard deviation, okay? When we don't know all of that information, when we know the population mean and when we know the population standard deviation, we can just use the z-score, right, or a z-table, okay? So the t distribution was thought up by that really smart guy that worked at Guinness, right? He was drinking too much beer, and he said, well, what if our sample sizes differ? What if we have different sample sizes? How do we know that we can use kind of probability that we'll get a certain event, right? Remember, he was testing the quality of the beer. And if he's getting a very small sample from a huge vat of beer, how can he be confident that that is a good sample? Or if he tests, maybe he tastes it and it tastes disgusting, right? How can he be confident in saying, we need to throw away this whole vat of beer because this little sample tasted gross? So he came up with the t distribution. It is based on sample size, okay? I'll come back to this one in just a minute. It's based on sample size because of the degrees of freedom, okay? The degrees of freedom. Now, this definition that I have right here is a little bit different than the definition that I had on chapter 8. Okay, the one in the slides from chapter 8 come directly from the book, okay? But if you remember, I gave an example about degrees of freedom, and we talked about, say, the first day of class in the real world. We're standing in the hallway, we're going into the classroom, and I'm having you all draw numbers from a bag to determine which chair you're going to sit in. The first person who draws has the most degrees of freedom. Their number has all the freedom to vary. Okay, as the first person draws the number, the second person has one less degree of freedom, right? Because one chair is taken. Now the rest of their numbers have a small portion of limited degrees of freedom. Okay, so here it says the degrees of freedom refers to the number of scores that are free to vary. Okay. Anyways, if we don't like that definition, or we're still kind of stuck on what in the world does that mean, that's okay. Our little formula for degrees of freedom is n-1. Okay, so if I tell you we have 20 people in this sample, degrees of freedom would be 20 minus 1. Our degrees of freedom would be 19. If I tell you I have 10 people in my sample, it would be 10 minus 1. We would have 9 degrees of freedom. Okay, and remember, in that table in the back of your book, or I've posted them here, you go by degrees of freedom. Okay, and you slide your finger down, and so say we find 9, okay, and then we see all these numbers across here. Okay, in our statistics class, we'll always do two-tailed, and convention for social sciences is 0.05. Okay, so in this example, in this table, we'd be using this column right here. All right, so we'd match up 9 and 0.05 for a two-tailed test, and we get here 2.282. Okay. Now this number that we are finding, this 2.282, if we remember, it's our critical values. It's the critical values that we're going to use to determine the rejection region. Okay, and we talked about these things, but I think until we start to put it into practice, it's not really going to make much sense. Okay, but once we do our t-tests, we're going to calculate some numbers, and then we're going to get to a point where we have to make a decision, and we're going to have to decide whether our data supports our hypothesis or whether it supports the null hypothesis. Okay, remember, our goal is to try and reject the null hypothesis, because the null hypothesis is telling us there is no difference in anything that we're going to find. Okay, so we want to reject that. We want to say, no, our hypothesis is correct. So we want our numbers to be in the rejection region, or we want our numbers to exceed the critical value. We want it to be bigger than the critical value. Okay. All right. So we have not done this yet. This is how we do statistics. Okay. We've put it into, or I guess I should say, I've put it into 4 steps. I don't know if this author does 4 steps. Some people do 7 steps, and some people do, well, I don't know if they do less than 4. That might be a little bit difficult. And I can't see here, I'm looking through my book real quick. I can't see off the top of my head how many steps he does. I can't find it, but that's all right. So we're going to go through 4. okay? And when we do the 4 steps, it makes sure that you're doing everything you need to, okay? So we can see here, step 1, we always want to state the hypotheses. Okay, that's plural right there. You want to state the null hypothesis and you want to state the alternative hypothesis. The purpose for stating the hypotheses is that once we get through our calculations, once we make a decision of ultimately either rejecting or failing to reject the null hypothesis, and we have to write a conclusion, it makes it easier to state that conclusion once you have stated the hypotheses. Sometimes our calculations, not in a t-test, but sometimes in other types of statistical procedures, it takes so long to get through the number crunching that we might even kind of forget what we were doing to begin with. And we might have to look back at the hypotheses and go, oh yeah, that's what we were looking at. Oh yeah, we were looking at, breastfed versus formula fed, or we were looking at, number of potato chips or whatever. So sometimes we forget that stuff. And stating the hypotheses just really kind of, it's there, it's clear, and it helps the conclusion writing so much better. Step 2, finding those critical values. Okay, this is a really easy step. Okay, it's just using this table. And like I pointed out before, where I said I use the example, if I had 10 people in my sample, my degrees of freedom would be 9, and I would slide my finger over to the two-tailed 0.05 column, and this right here, this 2.282 would be my critical values. Okay, so that's step 2. Step 2 is really easy. It's just finding those critical values. Step 3 is a loaded step. Okay, there's a lot. You got all the calculations you got to do. Okay, so step 3 is the mother load. Okay, this is where we're actually doing our number crunching. And then step 4 is just make a decision. We're either going to reject the null hypothesis or we're going to accept it based on whether it meets the critical value, whether it exceeds it, and it finds its way into the rejection region. Okay. All right. Any questions about steps 1 through 4? Anything like that? No? We'll just have to put it into practice to see how it works, right? Okay. All right, now take a deep breath. Okay, take a deep breath. We're going to get some formulas here, okay? But it's okay. We can do it. Okay, we can do it. So this is step 3, ultimately, okay? These are the formulas that we'll be using in step 3. Oops. So we have 3 formulas. All of them, well, these 2 here are going to feed in or give us numbers that are needed to calculate our t, okay? So we can look at our t here, and then we'll see different pieces. Sometimes I like to think of them like a puzzle, right? And we have puzzle pieces that we need to find. We have numbers that we need to find in order to fill into the formula, okay? So let's see, I'm going to get my draw up just so I can write a few things and kind of explain what some of these numbers are, okay? So this is ultimately our t that we're going to be finding and using, and that t value, that number, is going to be the one that we compare to the critical value. Okay, so once we get our t value, we're going to see if it exceeds or it finds its way into the rejection region. If our t-value is big enough and it goes beyond our critical value, then that's when we get to reject the null hypothesis. Okay, so ultimately the t-value is going to be our most important number in these calculations.
Sorry,
Okay.
can you repeat that again? I want to
Sure.
try to.
Sure. So remember when I was saying, because this is kind of, this is all from last week, right? And so remember, we're going to have our critical values here. And let's just use that one example from that I was using on this other slide. Okay. Well, right here would be negative 2.282. Remember on this slide here, I found that critical value just in our make-believe that I said we had a degrees of freedom of 9, and we had this right here, this 2.282, because it's a two-tailed and it's a 0.05, okay? So let's just pretend that those are our critical values, okay? When we go and we calculate all these calculations, we're going to come up with a t-value. This is going to equal some number, okay? And we're going to take that number and see where it fits in this distribution. If it's bigger or it exceeds, if it goes somewhere in here or somewhere in here, remember these are the rejection regions. Anything beyond the critical value is the rejection region. Do we remember that, Natalia? You're
Yeah, I'm just writing this down. Anything?
Oh, okay. Anything, or a t-value that exceeds a critical value, we reject the null hypothesis. Let's see, I got to shrink that down a little bit.
Okay. Yeah, sorry. I need to write this down because if not, I'll forget. So
no problem. And what we did talk about it last week in chapter 8, but I mean, one time talking about that does not necessarily always, it doesn't stick, and it doesn't really even make sense because it's kind of like, what are we talking about, right? And it doesn't start to make sense until we really start putting it into practice. Okay, so I completely understand where you are, okay? So when the t-value exceeds the critical value, reject, I'm just going to put the HO here, the HO, okay, the null hypothesis.
okay.
Okay, so let's see, I'm going to go back to draw now. So anything in here, we call this the rejection region, okay? Anything beyond our critical value is called the rejection region. If it does not exceed the critical value and we have a t-value anywhere along here, that is when we have to either fail to reject or we accept. Okay, so let me write that too, okay? Yeah, I realize you can't see that. How about right there? So when the t-value fails to exceed the critical value, we accept the HO or the null hypothesis. Oops. Okay. And we'll see that. We'll do this lots of times. Okay. Okay. Anything else, Natalia, or you want to see it?
I was just writing this down.
You wrote it down. Okay.
Yeah.
Okay, good. Okay. So we're going to get a t-score. Okay. And that's what this is right here, right? Our t-score. This right here is our sample mean. Okay. This is our sample mean. This is just kind of going over our symbols again. This is going to be the population mean. This will have to be given to us. There's no way we would be able to find this, okay? And it will be given to you. It will be in the word problem somewhere, okay? So the population mean. And then this right here, this is our standard error. We talked a little bit about standard error when we started talking about sampling distributions, and I went over the central limit theorem, and it was kind of that crazy, very philosophical, theoretical talk where you guys were probably like, what in the world is she talking about? Okay, and that's okay. That's okay. We just know we need to use standard error. Okay, so that's what that is right there.
Excuse me.
Uh-huh.
Simple mean is that the t or is that the whole equation?
One more time, Christy.
The simple mean is that only the t or is that the whole equation?
The sample mean?
Yes.
I'm not real sure what you're asking, but t will be equal to, right, the sample mean minus the population mean, and then we're going to divide it by our standard error.
Okay, okay.
Okay, so the sample mean we will calculate, we'll find it when we get our sample data. Okay, so this is something we're going to have to calculate. The population mean will be given to us. And then we are also going to have to calculate our standard error. Okay, so there's two things we're going to have to calculate here. This one, in every statistics from here on out, the denominator is the pain in the butt, I guess, if we want to think of it that way. Okay, this is your form of variance or variability, and it's always going to be the more complex of everything. This stuff up here, easy peasy, okay? The means are easy. It's always this measure of variability down here, okay? That's just gonna take more work to do. So standard error down here is found right here, okay? Sorry, that doesn't look like a very good arrow, but here's our standard error. And it's telling us to find standard error, you're going to use this is estimated standard deviation, and you're going to divide it by the square root of n. Okay, so to find standard error, we're going to take our estimated standard deviation and we're going to divide it by the square root of our n. Okay, n will also be there, we'll know n. Okay, we're going to know n. It's this one that we're going to have to calculate. This guy is right here. Okay, so even though I listed our formulas this way, right, we're really going to be working backwards, right? We're going to have to calculate this first in order to get this number so that we can find this one. And then once we get this one, we can plug it in here and then we can calculate our t. Okay, So this here is our estimated standard deviation. I'm just going to abbreviate that one, okay? Estimated standard deviation. And we've done this formula more or less, okay? It was a long time ago, right? Way back in chapter 4, I believe, we were doing this formula. The only difference was we were not doing the negative, we weren't doing this part, okay? We just had n down there. But we did this formula, okay? This time around, the only difference is we are going to add in there this n minus 1 at the bottom, okay, or in the denominator of this formula. And we do that because it just makes the estimated standard deviation a little bit larger, and which we could assume would be for the whole population. Okay, so it's just something that we do when we don't know the population mean or standard deviation, and we have to estimate it. Okay. Okay. So I'm not even going to go on to the other chapter, or sorry, the other slides yet. Okay, because we're going to do a couple of examples here. Okay. So I want to pull one from the chapter, from the book, so you all can look back at it also and see it all written out and see it nice and neat, so that you know you can look back at it, you can read through it, and I think it'll just help like solidify what we did and the steps and that whole process. Okay. If I could find one. Oh yeah, okay, we like this one. Okay, so I hate that I don't have my camera. Let me insert something real quick, just so y'all know where this example is coming from. Okay. Is page 199, oops, in the textbook, and it's I'm doing number 27, or it's 9.27. I don't know why they do that, 9.27. Okay. Now let me kind of tell you what it says, okay, if you don't have that in front of you. What you can do, if you're really bored one day, is you can test to see if you really get the amount of something you pay for that the package claims that it's supposed to be. Okay, and you can test it and see if, you know, their quality control is doing a good job or not, or are you getting gypped off, right? Sometimes we get little bags of chips from the vending machine and we feel like there's like nothing inside of them, right? We feel like there's no way that there's, you know, 9 grams or whatever inside of this bag. Well, you could test that if you wanted to, okay? So in this example, what this guy did was he got Snickers bars, okay, or different candy bars from the Mars Corporation, but I believe he got Snickers, okay? And on the package of a Snickers bar is it tells you how much Snickers you should get, right? And here it says that the Snickers bar claims to weigh 58.7 grams. Okay. Oops, I didn't mean to do that, but I guess that still makes sense, right? So the claim is that the Snickers will weigh 58.7 grams. So our author of the book, I believe he really did this, because I would believe that he would do this, went out and he collected he bought 6 different Snickers bars, okay, and he weighed them so he could test this claim. All right, I'm going to add another thing down here. Let's see. I don't want it. We could do that. That's fine. Okay. Wait, oh, am I? Oh, don't go back. Go back. What are you doing? Okay. Okay, so what he did was, I'm going to do X. Oh, no. Well, text box. Can't go wrong with the text box, right? So I'm going to put X here, okay? And because this is our variable. All right, let's underline it. And he went out and he collected 6 different, Snickers bars, and he weighed them, okay? The first one weighed 59.1. The second one weighed 60 grams. The third one weighed 58.6. That one weighed 60.2. This one weighed 60.8. And then you're really getting a lot for your money with that last one. It weighed 62.1 grams. Okay. So he wanted to see, does a sample of Snickers bars match the claim that the Mars company is telling you Snickers should weigh? Okay. And is it going to be statistically significant underweight? A cynical person might think, no, we're going to get gypped. They're going to give us less Snickers bar. Or someone might say, no, they're going to give us more. Okay, I don't know. So they went and bought 6 Snickers bars, and they weighed them, and these are their weights. Okay. All right. So here we go. Here's our data. All right. And so now we're going to start off with step 1. Okay. Step 1 in that other, on that other slide was state the hypotheses. Okay. And so this is what we will do. I'll start with the null hypothesis, okay? And the null hypothesis always states that there is no difference, right? And so this is kind of the hard part for some people. Some people really like the math and they don't like the word part of statistics. Some people like the words and they don't like the math, okay? There's definitely wrong ways to write hypotheses, but there are a lot of right ways to write it. There's a lot of different ways people can write in their own words what they think the hypothesis is, okay? So just remember, with the null hypothesis, they always state that there's not going to be a difference. So we could say something like this: there will be no difference among the means. This is a very generic kind of easy way to write the null hypothesis. For me right now, I would be okay if you wrote that, okay? I might push you a little bit. I might write next to it and say, well, what do you mean? What are the means? Okay. If you go up to UTEP, they're going to push you. They're going to want you to explain it more. Okay.
Would the means be the Snickers or which would be the means?
Yes. Good question. So, right, like, what are we talking about? What are we looking at? Right. And if we look back, remember, a t-test is the sample mean compared to the population mean, okay? So those two means that we're looking at are let's see, the means of the 6 Snickers bars and we could say like company claim. Oops, what did I do? What's wrong here? Snicker, oh, a C. There will be no difference among the means of 6 Snickers bars and the company claim. This one here, right, those 6 Snickers bars is the sample, right? And this company claim is the population mean. That's kind of weird, a weird way to think about it, okay? But that's just what we would use as the population. So the company claim, this will be our population mean. They're saying on average, your Snickers bar should weigh 58.7, okay? When we add up all of these and we find our sample mean, that will be the 6 Snickers bars mean, okay? So we're gonna see if there's a difference between the mean of our sample and the mean of the company claim, okay? Now, looking back over this, is this a great sentence? Probably not. If you're an English major, you might be like, okay, you could reword that. I'm not an English major. And so if you wrote that, I could see that you clearly know that you're comparing the 6 Snickers bars to what the company claim is, okay? This shows me you know what you're testing. All right. And there's lots of different ways you could write that. You could say there will be no difference between the 6 Snickers bars and 58.7 grams. You could say that. There's lots of different ways that you can write this. Okay. The alternative hypothesis, our research hypothesis, right? Oops. States what you think is going to happen, whatever you think your hypothesis is, okay? Now, we may not know what our hypothesis is with this one. We have no interest in this. This was just something that was given to us, so we don't have, a preference one way or the other. If you're a cynic and you think that companies gyp you off, then you might say, I think the sample mean is going to be less than the company claim, okay? If you are a positive, thinker and you like to believe there is good in the world and you're like, no, Mars is going to give us more Snickers than they claim, then you could write that I believe the sample mean will be greater than 58.7, okay? If you really don't know and you don't have any stake in the matter and you don't, you have no idea how this is going to go, you can say there will be a difference between, I'm going to type it a little bit different, there will be a difference between, the sample mean or the sample of 6 Snickers of 6 Snickers bars and the company claim of 58.7. Okay. You could even in weight, right? I mean, you can get really, I think the more detailed you are, the better. Certainly when you go up to UTEP, right? The more detailed you are is going to show you really know what you're talking about. Okay. Now, obviously, the more detailed you get, you could talk yourself into a wrong answer, right? You could start writing things incorrectly. So, but I kind of like to say, start off really simple. There'll be no difference in the means, or there will be a difference in the means, and then go back and fill it in after that, right? Difference in what? So that's where I put in weight, right? Because we are measuring weight. Okay, so there will be a difference in what? Oh, in weight between the sample mean. Okay, well, what's the sample mean? It's the 6 Snickers bars that we got. You could say, right, difference between the sample mean and the company claim. Okay, well, what is the company claim? 58.7. So that's one thing that I tell people, start off with a very basic sentence and then try and go back and fill in those details. Okay. All right, so this is not the easiest stuff here, writing out our hypotheses. I'm fully aware of that. So it takes practice, and that's what we will work on. Okay, we'll work on that. So that's step 1. Step 2 is our critical values, right? Our critical values. So this is having to use that table. Well, why didn't that work? Oh, the table, the t-distribution table, to go and find what our critical values are. Now, if you remember, you have to find a number in order to get our values. What number is that? Our degrees of freedom. Okay, we have to know degrees of freedom in order to find any critical value down here. Okay, so critical values. Oops, I didn't mean that to be like that, but that works out well too. Let's do this one like that too. I'm going to put parentheses, degrees of freedom right there. Okay, you have to find degrees of freedom. So our degrees of freedom is n minus 1. What is our n in this example? Anyone have a guess?
Is it any of the X's?
That's right, it's all of them. Right, we add up our number of observations gives us n, right? Is that what you were going to say?
No, but now I know.
Okay, no, I didn't mean to put you on the spot. Remember, n is our number, right, of our, I mean, sometimes I say number of participants, but these aren't people, right? These are Snickers bars. So our number of observations, or the number of data points we have. And so in this example, we have 6, right? 1, 2, 3, 4, 5, 6. So n is 6 in this example. Okay, I put a little n. It really doesn't matter, guys. N is n at this point. Okay, so 6. So degrees of freedom would be what?
Oh wait, so it's the how many there are, like how many. I thought it was adding up all the data. I'm sorry.
No, that's all right. Remember, when you add them up, that's going to be our sum of x.
Okay, but this is just the n, which is how many there are in the
How many
data.
there are. That's right. That's all it is. Yeah, N is just how many there are. And when we add them all up, that's going to be our sum of X. Okay. So N is 6. Degrees of freedom is N minus 1, right? N minus 1. And just in case, remember up here, degrees of freedom is N minus 1, where N is the sample size or the number of, observations you have, okay? So we have a degrees of freedom of 5, right? 6 minus 1 is 5. We're always going to be in this right here, two-tailed 0.05. So we just slide our finger over and we see here our critical values are 2.571. Degrees of freedom of 5. And that column right there, 2.571. Oops, did not mean to do that. Oh my gosh.